Hello, everyone. So this is a video about Euclid's algorithm and Bezout's identity. If you're following my book, Number Theory and Geometry, then this is in topics in sections 2.6 and 2.7. Okay, let's get to it. So first, just reviewing some definitions that we've seen before. We've seen divisibility. To integers, we say that A divides B if there is an integer m such that B equals A times m. And we've defined a GCD. A GCD of two integers, not both zero, is a number d, which is a positive integer that is a common divisor of a and b, and it is also the largest divisor. So if there is another divisor of a and b, then that divisor has to be less or equal to the greatest common divisor. Great. We quickly saw that computing a GCD can be very time consuming if you try to do a brute force algorithm, which is computing all the positive divisors of A, all the positive divisors of B, and find the largest positive common divisor. So instead, what we learned is that Euclid, more than 2,000 years ago, came up with what we call Euclid's algorithm, which is a very efficient way of computing GCDs without computing all the positive divisors or computing a prime factorization of a number. Great. So this is the basis of Euclid's algorithm, is this theorem, which tells you that if you are trying to compute the GCD of A and B, and you do long division of B by A, then you are going to get some Q and R that are in this that satisfy an equation like this, that B is AQ plus R. That would be usually the quotient and remainder of dividing B by A. But at any event, what we proved is that the GCD of A and B is the same as the GCD of A and R. So the GCD of B and A is going to be the same as the GCD of A and R in this equation. So for example, let's do an example here. So if I want to know compute, what is the compute the GCD of 337 and 271. Okay, so what we do is compute, start doing long divisions. So we have here a long division of 337 by 271. 271 goes once into 337, and I get a remainder of 66. Then what we do is take 271 and divide it by 66, because, well, we'll see in a moment why this all works. This is 66 times 4 plus 7. Then I take 66 here and divide it by 7. That gives me 66. That will be 7 times 9. That's 63. Plus 3 is 66. And then 7 is 3 times 2. That's 6 plus 1. And 3 is 1 times 3 plus 0. As soon as we get 0, that means that right above it, this number is the GCD. So the GCD is 1. Okay, why is that true? Because of the theorem. The theorem tells me that here, 337, the GCD of 337 and 271 is equal to the GCD of 271 and 66. Okay, that comes from the first equation. Now, the second equation tells me that the GCD of 271 and 66 is the same as the GCD of 66 and 7. So that tells me that 66 and 7 have the same GCD also. The third equation is going to tell me that 66 and 7 have the same GCD as 7 and 3. And the fourth equation tells me that 7 and 3 have the same GCD as 3 and 1, which is obviously 1. Or if you go to the next equation, that's the same as the GCD of 1 and 0, and that we know it's 1. Okay, so if you read it from the top, this tells me that the GCD that I wanted equals 1, well, which is what we wanted to find out. Okay, let me do it again, but with some positive, some GCD that is not just 1. So here's another example where I'm going to take now, what is the GCD? I want to compute the GCD of 221 and 91. So I do the same thing. I do long division. Whoops, not 2 to 2, 2 to 1. I'm going to divide by 91. That's 91 times 2 plus a remainder of 39. Then I take 91 and divide by 39, and I get a remainder of 13. And then divide 39 by 13, and that is an exact division. So the GCD is right here. The GCD is 13 in this case. And again, this works because the first equation tells me that the GCD of 221 and 91 is the same as the GCD of 91 and 39, which is the same as the GCD of 39 and 13, but that is the same as 13 and 0, which is 13. Okay, so we found the GCD of those two numbers. Great. So now what we're going to do is solve what we call Bezout's equation. So Bezout's identity is an equation of this form. So given A and B integers, the goal is to write the GCD of A and B as a linear combination of A and B. So the goal is to find integers A and B, X and Y rather, so the ones that we don't know yet, X and Y, such that AX plus BY equals the GCD of A and B. Okay, so in this case, for example, above, we would like to express 13 as a linear combination of 221 and 91, or in this other example, we would like to express 1 as a linear combination of 337 and 271. Let me start with an easy example. So an easier example. So for example, let's find the solution of Bezout's identity for A equals 5 and B equals 7, i.e. Find integers X and Y such that let me just write the bigger number first, equals the GCD of 7 and 5. Okay, so what we do this in steps. So step 1, we're going to first find the GCD of 7 and 5 using Euclid's algorithm. Okay, so we do 7 is 5 times 1 plus 2, and 5 is 2 times 2 plus 1. And I know I'm done because 2 is 1 times 2 plus 0. So this is the first step where we found the GCD is 1. Okay, so this tells me that the GCD of 7 and 5 is 1. Now in step 2, what we do is reverse the Euclid's algorithm to write 1 as a linear combination of 7 and 5s. Okay, so I want to eventually find a solution to this equation. So now I want to find solutions of 7x plus 5y equals 1. So I'm going to start with this line here and solve for 1. Okay, 1 is 5 minus 2 times 2. And then what I'm going to do is solve for 2 in this equation and plug in that 2 over here. Okay, so I'm going to write here that 2 is 7 minus 5 times 1, which comes from this other equation. and use that information in my equation above to write that 1 is 5 minus 7 minus 5 times 1 times 2. And now use the distributive property without multiplying everything through, just to collect 5s and 7s. So this first says minus 7 times 2, minus 7 times 2, and then this is a plus, so this is 5, and let me just spell it all out, what it actually says. This is 5 minus 7 times 2 plus 5 times 2. And now I'm going to collect the 7s and the 5s for clarity. So this is 7 times 2 plus, and this is, there's a 5 here, and there's 2 more 5s here. So I have 3 5s. So this is 5 times 3. So if you put it in terms of, like you see, we wanted 7x plus 5 times y, I'm going to write it as 7 times minus 2 plus 5 times 3. And you see that this says that minus 14 plus 15 is equal to 1. So that is a solution. So now just step 3, just read off the solution that we just found. From here, it says that 1 is 7 times minus 2 plus 5 times 3 equals 1. And therefore, x equals minus 2 and y equals 3 works. Okay, so that is my solution, and I'm gonna maybe do a box around my solution right there. Okay, very good. Let's do another example now, using what we found before. Maybe with this example right here, I'm going to copy it. Where I have my tool to copy there. I'm gonna grab all this like this, copy it, and bring it forward. Okay, very good. And so now I'm going to, the question now is find a solution of Bézout's. So I'm finding a solution of 221x plus 91y equals the GCD of 221 and 91. Okay, so in this case, we already found 13 is the GCD, so I'm trying to solve this equation. All right, so now what we can do is we have already done step 1, which is, so this would be what we called before step 1, which is Euclid's algorithm. And step 2, I want to reverse Euclid's. So start with the last equation. 13 is 91 minus 39 times 2. And now what I do is plug in. I'm going to use this equation and plug it over there. You solve for 39 and plug in 39 over here. Okay, so this is 91 minus 221 minus 91 times 2 times 2. So that is, is 91 minus 221 times 2 plus 91 times 2 times 2, 4. So this gives me 221, I keep writing 222. 221 times minus 2 plus 91, and you see there is 191 and 491, so there's 5 91s. Okay, so that is the solution we wanted, because now that tells me what is the solution we just found, that 13 is 221 times minus 2 plus 91 times 5. So x equals minus 2 and y equals 5 works in the equation above. So that is my solution to Bézout's identity. Okay, let me do it one more time with a little bit more complicated of an equation. let's do this one that has several steps, just to show you we see it several times. So I'm going to copy all these steps we've already done. Let's move them over to another example over here. Example. I'm going to copy and paste. And this is just going to be here. It's going to be my first step of trying to solve find a solution of 337x plus 271y equals the GCD of 337 and 271, which in this case we see that it is 1. In this case, the GCD is 1. So step 1 that we've already done, that's Euclid's algorithm. And now for step 2, we reverse Euclid's algorithm. So we start from this line. 1 is 7 minus 3 times 2. Now I'm going to use this equation over here. I'm going to solve for 3 and plug it in. So this is 7 minus 66 times 7 times 9 times 2. Okay. This is, if you keep track of what's going on, oops, 766 minus 7 times 9. That is going to be how many there is, let's see. Yeah, 9 times 2, 18, plus 1 more 7, that is 19 sevens, minus 66 times 2. Okay, or let's write it in front, the coefficient. So 2 times 66. So I'm keeping track of 7s and 66 here. Great. Now I take this equation over here, and I'm going to use the 7 and plug in 7. Okay, so this 7 here is going to be substituted for this 7 over here. So this is 19 times 271 minus 66 times 4 minus 2 times 66. So this is 19 times 271 minus 19 times 4, 19 times 4 and another minus 2. It turns out, I have my cheat notes here, this is 78 times 66. Okay, and there what I did is put together 19 times 4 plus 2, that is 78. Great. And then last, I'm going to use this equation. I'm going to solve for 66 and plug it in over here. Okay, so the last equation that I get is 19 times 271 minus 78 times, and substitute 337 minus 271. And then what I get is, if I collect my first 271s, there is 78 and 19, that is 97. And then 78 times 337. So in the step 3 now, let's rewrite that equation. So what I got from the step 2 is that 1 equals, I want 337 first. So I'm going to write minus 78 times 337 plus 97 times 271. And then I want to really write it like this. So I'm going to write 337 times minus 78 plus 271 times 97. So this tells me that the solution that I wanted is minus 78 and y equals 97. And that's my final answer. Okay. So there we found another solution to Bézout's identity. Great. So I'm not going to write a proof of the following theorem, but what this says is that we can always start with Euclid's algorithm and revert it to find the solution of Bezout's identity. So what I am going to do is write it as a what I'm going to do is write that as a theorem. Okay, so I'm going to write it as a theorem that what we call Bezout's identity. Okay, and Bezout's identity says that let A and B be integers, not both 0, because I'm going to do a GCD of them, such that D is the GCD of A and B. Then what just happened is that this algorithm using Euclid's and then Euclid's backwards tells me that there exists integers R and S such that A times R plus B times S equals D. Okay. In other words, the Bezout identity AX plus BY equals GCD of A and B has a solution in integers, namely X equals R, Y equals S. Okay, so that is what we just proved is this theorem that we call Bezout's identity, that this algorithm yields a solution of this identity. We haven't proved this. It's not worth writing a formal proof of this. It's just a lot more symbols than it's worth. I think the examples that we just did are more illustrative of the fact that the algorithm always works to find the solution of this equation. Okay, so this has some very important corollaries. So the first corollary of Bezout's identity, of the theorem that is Bezout's identity, is the following. It's the following. Actually, so let me just write a remark first. So here's a remark. The definition of GCD, remember that we defined the GCD of two numbers as is a number is a positive number that is a common divisor, and if there is another common divisor, then n is less or equal to d. But we did not prove, we did not assume in the definition or prove that in fact any common divisor of A and B divides the GCD. You see, in the definition, it just says that is the greatest. It's something about size. It's the greatest common divisor, but it doesn't say that n actually has to divide that divisor. That happens, of course, like if you have, let's see, example. If I have, let's see, what's a good example? So I would like something like 4 times 7, so like 28 and 14. Let's actually do 14 times 5 maybe. 28, 14 times what do I want here? So 14 times 5. Yeah, 14 times 5 works 70. Okay, then the GCD of 28 and 70, because, well, 28 is 4 times 7, and 70 is 7 times 2 times 5. The GCD is going to be 14, right? But any other divisor, so the GCD of 28 and 70 is 14, and 7, for example, is a common divisor of 28 and 70, and 7 divides 14. Likewise, 2 is a common divisor of 28 and 70, and 2 divides 14. So every common divisor divides the greatest common divisor, but that is not something that comes out of the definition. So we're going to use Bézout's identity to actually prove this fact. So let me just prove the following corollary. Let A and B be integers, not both 0. With, let's say, the GCD of A and B is D. And suppose that N is a common positive divisor of A and B. Then N is a divisor of D. Okay, so how are we going to show that? Here's the proof. Since they're both not 0 and we have the GCD, by Bézout's identity, the Bézout's equation, AX plus BY equals D, has a solution in integers. So X equals R and Y equals S for some integers R and S, so that AR plus B S plus B S equals D. Okay. Now let N be a divisor of A and a divisor of B. Then N also divides AR plus BS, because A is any that's a divisor of A, so this is A prime times N, and B is some B prime times N for some A prime, B prime integers, and therefore D will be AR plus BS, will be N times A prime times R plus N times B prime times S is N times A prime R plus B prime S. And since this is a combination of integers, this is also an integer, and this implies that N is a divisor of D. Okay, N times an integer is equal to D, therefore N is a divisor of D, which is what I wanted to prove, that the common divisor of A and B, N, is also a divisor of D. Great. So that is one thing. And the other thing that is super important, which is going to be perhaps the most important theorem in all of our class. This is sometimes called, it's so important, it has a name, Euclid's lemma, or sometimes, because it is so important, which is like the key to prove the fundamental theorem of arithmetic, is the key to prove unique factorization of integers into primes. So sometimes we call this the fundamental theorem of arithmetic. Okay, so maybe you want to call it the fundamental lemma of arithmetic, because this is not the actual theorem that is unique factorization. But again, this is so important that sometimes I would call itself the fundamental theorem of arithmetic. So let A, B, C be integers such that A divides B times C. And suppose that the GCD of A and B is 1. So A divides B and C, and A and B are relatively prime. Then A divides C. So this says that if I have a number dividing a product, and this number and that number are relatively prime, then this number has to divide this second number. Okay, let's see some examples. So for example, let's say 2 divides 6. 2 divides 6, and here, so here A is 2, B is 2, C is 3, so that 2 is dividing 2 times 3, and in here A, maybe I should write it exactly like in the statement. So pick B to be 3 and C to be 2, so that the GCD, it is true that the GCD of A and B, the GCD of 2 and 3 is 1, and therefore, because of this, because all of these conditions, 2 must divide 2, which is A, must divide 2, which is C. Okay, so it is true in this case that if 2 divides 3 times 2, 2 divides one of the factors. Let's see, for example, so how about for example, let's say 6 divides 30. Okay, here A is 6 and B is 5, while C is 6. This actually does make it a little bit more complicated. Let's say 30 instead of 30. Let's write 30. Let's write 150, say. Okay, so this is 150, so that yeah, so I can write 5, and let's write to be 30, so that 6 is dividing something like 5 times 30, but the GCD of 6 and 5 is 1, so we must have that we must have, so 6 and 5 are relatively prime, 6 divides the product, so then 6 must be a divisor of 30. Okay, so all of these things together with the corollary, what that says is that 6 must be dividing 30, because 6 does not divide. 6 and 5 are relatively prime. Okay, all right. Very good. So let's prove that that corollary. So again, the corollary says that if A, B, and C are integers, such that A divides B and C, and the GCD of A and B is 1, then A divides C. Okay, let's prove that. Okay, so how are we going to use Bezout? Bezout's identity comes from the fact that it comes in handy because there is a GCD in the sentence, in the assumptions. So since the GCD of A and B equals 1, Bezout's identity implies that there are integers R and S such that A times R plus B times S equals the GCD, in this case 1. Okay. Okay, that doesn't have anything to do with C, so I'm going to multiply through by C. Okay, then now multiply this equation through by C. Then what I get is that, well, I'm going to write it like this: ACR plus BCS equals C. Okay, I just multiplied by C. So there is a new C factor here, a new C factor here, a new C factor here. I used a distributive property along the way, but that holds. Okay, so now you see that 1, A divides ACR, right? Because A is, or ACR is a multiple of A, clearly. And A divides BC by assumption, right? By assumption, A divides BC. So A divides BCS. Okay. And together, so this two facts together, this fact and this fact together, tell me that A divides all of this. So thus, this does tell me that A divides the left-hand side, ACR plus BCS. So therefore, thus, A divides ACR plus BCS, which is C. So A divides C as well, which is what I wanted to prove. That's it. Okay. It tells me that A divides C, which is the conclusion that I wanted to draw. Okay, and again, this is going to be very important in proving the, for example, the fundamental theorem of arithmetic, because what we're going to say is that when we have, so what's going to happen is that we are going to have, for example, to prove uniqueness of prime factorizations, this lemma or this corollary is super important, because when we have an equation, suppose there was no unique factorization of primes, and suppose there was some n that is both p times q, and also it has another factorization, let's call it p prime times q prime. So suppose that n, an integer, is p times q, and it's also p prime times q prime, where p, q, p prime, and q prime are primes. By the corollary, well, before I use the corollary, but see, this equation implies that p is a divisor of this number, right? So p divides PQ, which is P prime times Q prime, then P divides P prime times Q prime. And if P was not one of those primes, suppose, and if P was not P prime, and these are primes, then the GCD of P and P prime would be 1. And now by the corollary to Bézout, that would imply that P divides a product and P prime are relatively prime, then P has to divide Q prime. Then P divides Q prime. But these are primes, so then P has to be Q prime. Okay? So even though we had assumed, or if we were trying to see if these were different factorizations, this is telling me that actually P and Q prime are the same. So I could factor them out, and then this is going to tell me that Q and P prime are the same, right? So this also tells me then that Q and P prime are the same, and therefore PQ and P prime Q prime are the same prime factorization. So actually, I haven't found a new factorization, and in fact, I've proved that any factorizations of two primes, or a number that is factored as a product of two primes, have to be exactly the same factorization. We will generalize this to prove, actually using induction, we will prove that this happens for any type of factorization. There is exactly one unique factorization. And the key here, again, is the corollary. The corollary is what has helped us do that difficult step. Okay, so I will stop here. In the next lecture, I will talk about roots of polynomials and solutions of lines with integer coefficients.